there. So there is no problem. I will looking into that. And so can we start? Little man, can I start? Okay.
Alias, can't you see the chat?
Yeah.
Yeah. Okay.
So please don't post anything in the chat. I can't see that. You can speak up, no problem, or share the reactions. Okay. So Hall effect in semiconductor. Okay. So this is discovered by Edwin Hall in 1879. So you guys want to see Edwin Hall now? Yeah, this is his picture. Is it visible now? Any problem is there? My screen actually some problem. Okay. Yeah. This is the one Edwin Hall. He discovered the Hall effect. And before going to the definition of Hall effect, let me say something. So for a while, I am stopping the sharing. And I will reshare from here. Okay. Yeah. So you can see this now. Anyone please speak up.
Yeah, it's visible. It's visible. Yeah.
Yeah. So this is a small, what you can say, small conductor. This one is placed on the top of a table. I think some problem is there. Can you see this now?
Yeah. It's visible, Alias. Yeah.
Yeah. Okay. I can't see that. Okay. You please speak up. Okay.
Yeah. Okay.
So this small conductor is placed on the top of a table. You can see now. It actually is in 3D. So you understood, right? So now you please close everyone your eyes and I will say something. So please try to picturize that in your mind. Okay. So yeah. So a keyboard is placed on the top of a table and there are two small sides are there and top is there, bottom is there, front and back is there. So you please take a battery, please picturize that and connect two wires to the small faces. Okay. Then in the front you place a north pole and the back also you place a south pole. Then you can see that on the top and bottom there appears a potential difference. Okay. So that is known as Hall effect. So now you please come back. I hope that I understood.
Yeah.
Okay.
Yeah. We can proceed.
Basically some problem is there, I think, with sharing. Let me try to connect. Please wait again. Yeah. So this is what when a magnetic field is applied to a current carrying conductor in a direction perpendicular to that of the flow of the current, a potential difference or an electric field is created across a conductor. This phenomenon is known as Hall effect. As I told earlier, we applied a current in the conductor and placed a magnetic field that is achieved by placing a north pole and south pole. And the other phase that is perpendicular to both current and magnetic field, we can see a potential difference. That is known as the Hall effect. So I hope everyone understood this. So we can see in detail, no problem. Before going to this topic, we require some basic equations. I think that everyone knows this equation. First one, I is equal to A drift velocity into En. And second equation, J is equal to conductivity into electric field, and next mobility is equal to drift velocity by this one. Okay, electric field. So I know, I hope everyone know these equations. We want to know, we want to use these equations interchangeably in this topic. Okay. So I will assign some members to remember these equations. So it will be easy for me to pick up that. Let me assign. So Amal Raj, first equation you should hold, and
Okay.
Ashwin second equation, and Ben third equation. Okay. So I will be calling your names. So you should speak up the equations very fastly. Okay. Is that okay? Okay. Yeah. So, and one more thing, you may be familiar. Yeah, you of course may be familiar with the Fleming's left-hand rule. This is of course when there is a for a charge particle, when there is a velocity and magnetic field, and the force will be in the direction of thumb. You know that. Okay. So I will stop the sharing and go to the derivation of Hall voltage now. Okay. Yeah. Yes. So you can see this screen, right?
Yes, it's visible. Yeah.
Yeah. So in the first screen, I will be going some fast. Okay, no problem. So I shown that a conductor is placed on the top. So I took some screenshot from there. So I marked the dimensions, length, width, and breadth, or anything you can like. I placed for width and height. So these are other screenshots from other sites. Okay. Okay. So this is how we applied. We placed a battery here. So placed a battery here and applied the current in this direction. So I marked the current direction on the top. Basically, current means here it is positive and here it is negative. So electric field direction is also the same current. Okay. So, and one more, we applied magnetic field also. So two things we are applying on a conductor. First, we are applying a current and magnetic field. So please keep in mind that these two things are we are externally applying to the current carrying conductor. So or the conductor. Now I am taking the case of conductor. Later I will be coming to the semiconductor case. For easy, we can deal first with the conductor. So okay. So this is the top view. You can see right now. Asta, you can see. Asta, hello. Asta is there. Hello. I think she's undoing. Okay, no problem. So this is the top view, and here we pass the current, electric field, and magnetic field also. Now we'll be deriving the equations. So you can see that two agency, external agency, we are applying, and we all know that in the current conductor there will be electrons. Yeah, charge carriers will be mostly electrons, mostly not electrons. So when an electron is there, this is an electron, and we applied a electric field is in there. Okay. So Ashwin, what will happen here? Ashwin Shekhar. Here there is an electron. We applied a electric field, uniform electric field. Okay. So what will happen?
Current will flow.
Yeah, it will face a force opposite this direction. And one more thing I am adding. What if there is an electron and there is a magnetic field? In this case, what will happen, Ben? Now say that electron is at rest. It is not having any velocity. So what will happen?
No force will act on it because of the magnetic field, because the electron is stationary.
Yeah, electron is stationary, but that is not the case. Electric field not required any velocity. It can act on directly, but magnetic field requires some velocity. That difference, understand? No? Okay. So I hope that everyone understood this point. So we understood that these two agency required a charge particle to act on. Can this act on stationary, what we can say, atoms, Ben?
Elias, can you please repeat the question?
Can this two electric field or electric field and magnetic field can affect a non-charged particle or just an atom? There is no charge at all.
Since the atom is neutral, the electric field can't affect.
So these two forces required if what again charge particle needed in order to act. So we can look into some detail. So now we got some idea that in order for these two force or the driving force to act, there required a charge particle. So in order to study this conductor effect, we can look into a single electron case, and later we will be assuming the total charge carriers in the conductor. Okay. As I told earlier, I marked an electron and electric field is in the direction I noted above, this direction, and there is an electron here and magnetic field in the Z direction. Okay. Now, as Ben told earlier, Ben not Ashwin Shekhar, okay. So, electron will face a force in this direction due to electric field. Yeah, right now? Yes. And so electron will be acquiring a velocity in this direction. Yeah. And we give some magnetic field in the direction Z direction. So according to Fleming's left hand rule, where will be the force? So this is the one electron is there, and this is the B direction, and this is the B direction, velocity direction. So force will be V cross B, that will be upward. Yeah, right? Yeah, this will be upward. This is the force due to magnetic field. And this will be upward for positive particle. Now it is an electron, so that force will be in the downward direction. So all the electrons in the conductor will face the same force. So this is the case of one electron, and the next electron also same force will be there. In general, I can say that all the electrons will be pushed down, right? So all the electrons in this conductor will be pushed to the bottom of this solid, or we can say that. Now Mayuga will come and ask me. I may add some characters, don't take it personally, okay? Now Mayuga will come and ask me. You can see that in this y direction, there is a unbalanced force. Yes, right, Mayuga? Hello? You please speak up, okay? Yeah.
Hello?
You can speak up. If you don't know, answer means you can say no problem. I will be doing that. Okay. So there is an unbalanced force in this y direction. Yeah, Mayuga?
Yes, yes.
Yeah. Then I will ask you one thing. Can this electron come outside of this conductor if there is an unbalanced force?
If it is greater than the work function, then it can come out.
Yeah, it's greater than work function, it can come out. I will add. I will say one more thing. When there is a here, you can see this is a conductor, and there is electrons randomly distributed here, and we applied some force, and we move all these electrons to this side. So we studied that there will be positive charge appearing on this side due to the charge separation. Yes, Mayuga? Hello?
Yes.
I think you know this by induction. You can see that when there is a charge separation, some force or some particles, positive charge, not particles, positive charge will appear on the other side. So in this case also, you can see that in this y direction, I am taking y direction only. X direction, you please leave. Now I am taking y direction. Y direction, there is a net force due to the magnetic field effect. And you can see that all the electrons are pushed to the bottom of this container. Okay. So there is a charge separation. Earlier, the electrons was randomly distributed. Now the electrons are pushed to down. So there is a charge separation is there. So we can see equal positive charge on this top. Yeah, Mayuga?
Yes.
Hello?
Yes. Hello.
Yeah.
Hello. Okay.
Yeah, you clear now? This point
Yes.
clear?
Yeah. Yeah. It's
Yeah.
clear.
Now you can see that there is a positive charge is there and negative charge is there, and there is a separation between positive and negative charge. So electric field can appear in that also in y direction. Mayuga?
Yes. Yes.
Yeah. So positive, from positive to negative, there will be an electric field. This is not this electric field. It is different from this electric field. This is induced electric field. Okay. So let me say one more thing. One more times I will repeat thing. So so we studied a single electron case, and we see that due to electric field we applied, we connected the battery now. So we connected battery, and there is electric field. This electric field. So that electron will acquire some velocity. When it acquires some velocity, when told that magnetic field can only affect in charged particles that have velocity. So now there is velocity. So magnetic field can affect on this particle. As a result, these all electrons will be pushed to down. So all these electrons will be located at the bottom of this conductor. As a result, there is a charge separation, and positive particles on a positive charge you can see on this top. So when there is a charge separation, you can see an induced electric field. So let me add one more thing. Okay. So you can take this electron out here, and I told that magnetic field force will be down, and you can see that here there is a new induced electric field appear. So that force due to that electric field will be upward direction. Mayuga, now it is balanced, right? Sorry, induced. Now it can be
Yes.
balanced, right? So
Yeah. It's
electrons won't be coming outside from this conductor. So an induced electric field appear there. So to our story, one induced electric field will appear. So that this force can be balanced by this induced force. So that I hope that is everything clear this point. In short, we can say that in equilibrium, we can say that these two forces will be balanced. So F induced will be balanced by the magnetic force. So Ben, please say me the magnetic force equation here. Ben, hello? No, I will call another member. Okay. Whom I will call? Okay. Yeah, Donna. Hello.
Yeah.
Donna, hello. Yeah.
Hello.
Yeah, Donna, can you hear me? Hello.
BIL sin theta.
Yeah, no, basic equation you can say that Q into V cross B. Yes, Donna?
Yeah.
Yeah, and you can see that you can also say this is Q into induced electric field. So you guys don't worry, okay? I will ask some questions for in order for class to continue, okay? That's only purpose. If you don't know means you can say no problem. So I cancel these two equation and this 2Q, and we can say that it is VB. We not need of cross product. We assumed this directions and all everything okay. So we can say it is VB, and please note that it is not the voltage, it is the velocity. Okay, and we can say this is the induced electric field. This one, induced electric field. Yeah, and I will ask one more thing. When here there is an electric field is there. 2 points I took, and between separation is L and A and B. Here. So whom I will ask next one? Fahad Nawaz. Okay. Fahad?
Yes, ALIAS. Yes.
Yeah. So I applied there is a uniform electric field is there, and 2 points I took, and the separation is L. So what is the potential difference between that 2 points?
E by L.
Yeah, good. E by L. So you know this equation. Yeah, right? So
Yes.
in this case also, yeah, in this case also, Fagad, please go hold. Okay, I will ask you one more thing. In this
Okay,
case
okay, okay.
also, you can see that there is an electric field is there, and this height, what we took this height, you can see. You look, this is we took as h, right? So
Yes.
this is h, and there is an electric field is there. So what is the potential difference between this? Let me
E
took
by
this
H.
and this. Yeah. So VAB in that case is E induced by H, right? Fahad, are you there?
E by H. Yes.
Yeah.
Yes, yes. E by H.
Yeah. We can call this VAB as the VH, whole voltage. Okay. E induced be there, E induced and by H. So, and E induced I substitute here, and this VH into H equal to VB. Is there any problem? Let me check. Is everything okay now? Hello?
Yes, it's correct. It's correct. Yeah.
Yeah. Yeah, okay. Okay. So VH equal to VB by H, right? So this is the velocity, magnetic field, and height of this conductor. And I will say, on this starting, I assign some equations. So Dan, what is your equation?
Dan wasn't assigned an
Actually,
equation.
you didn't assign me any equation.
That first equation whom did I assign? I think I should assign.
Amalraj.
Amalraj.
Yeah, Amal.
Amalraj.
Okay, sorry, I forgot. Amal, what's your equation? Amal, hello. Is there Amal here? Amal Raj, hello. No problem, leave it. So I'm
Yes.
taking the Amal equation for some
Hello?
time. Okay, Amal, I will take that equation. So current equation is equal to A into V. This is the velocity into En. Okay. So we have here this V is there, and here also V is there. We can substitute this one, and I am going to substitute for velocity. So we can see this En, right? Yeah. Let me add one more thing. Please wait, guys. I will add one more thing. Yeah.
Alias?
Hello. Am I audible?
Hello?
Hello. I think there is a problem with this. Equal to
Voltage
V.
equals to electric field into height, right?
Yeah. Sorry, guys. There is a problem. This equation should be somewhat. Fahad. Okay.
Yes, yes.
VAB is equal to.
E into L, I guess. Sorry.
Oh, no problem. VAB by L. You made me some problem. Okay. Okay, no problem. So thank you for that one. Okay. So H will be in this. Okay. So you guys can see this mistake while deriving. Okay. So what is our area here? Fahad, what is the area? Is the W into height, right?
Yes.
So in short, we can write this WH into E. We can cancel this, sorry. And we can write this IB by EN. EN into this W is there. Okay. This is our equation for whole voltage. So I will say one more thing. In this case, we applied to external agency, that is the magnetic field and the current we applied. Okay. But we got this electric field induced is what we got. The external agency are these two only we supplied, and we got this as a result of that. And the force due to this, this will balance the magnetic field, and we can get, by deriving, we can get this whole voltage as IB or VH equal to IB. In general, we can talk this equation as IB divided by N into T net. Okay. So assume T is equal to W. In general, I will hold this equation. So this is the first equation. Okay. Okay. Who is that? You want to talk? Okay, no problem. So I'll move. And we are, hello, can you please mute that? Pradeep Kumar. Hello. Pradeep Kumar, hello. Lindu ma'am, can you mute him?
Actually, Lindu ma'am is not here now. She is in another meeting.
Yeah, no problem. Okay.
Okay.
So yeah, Pradeep Kumar, thank you. Yeah, I'll give you a chance. Okay, now you please hold on. So VH is equal to IB by net. This is the equation. So will I assign another member to remember this one. Now Sanjana DV, you can hold this equation. Okay, VH is equal to IB divided by net. You please hold this equation. I will asking you. Okay. So I am calling this 1 by NE as the RH or the whole coefficient. Okay. Is Asta there? Hello. No. Yes, one. Sarangi, hello.
Yeah.
Yeah. Do you have any problem that I am 1 by NE? I am calling this RH.
Sorry?
Do you have any problem? I am assigning this 1 by NE as RH. Just as whole voltage RH.
No.
Okay. So Sarangi, no problem. So we can call this RH as 1 by NE. As we are somewhat new gens, we can 1 by N is one somewhat small equation, right? So we will be, what you can say, express this equation in other terms. As I told earlier, induced electric field is V into B. You can see here, this one, this equation. And I'm adding E into V, and the current density is equal to I by A. Or you can say current equation is A into V into E. So you can cancel this. And instead of this 1 by NE, you can write this as J by V, this velocity. And instead of this velocity, you can substitute this, and this is En by J times B. So this is also an equation of for RH. So I assign another member for holding this equation. Salvin Saji is there. Hello. Salvin?
Yes, I'm here.
Yeah. So you please hold this equation, okay? 1 by
Okay.
NE and En
Alias,
by
can you explain
JB.
once more from the introduction of whole coefficient?
Yeah, whole coefficient. I just called this 1 by NE as whole coefficient. No purpose. I am calling this 1 by NE as whole coefficient, right? And instead of that, whole 1 by NE, I took this E. We earlier derived that induced electric field is nothing but whole voltage in so velocity into B. We balanced that two forces and we got this equation. And instead of this current density, I took this as I by A, and we know that I is nothing but A into V into En by A. So that we can cancel that A, and instead of 1 by NE here, NE is there, we can write J by velocity. So velocity will be coming up, and instead of this velocity, I took thus En by B. Is that clear, Salvin?
Yeah, good.
Yeah. So these two equation you need to hold, okay? 1 by NE and E induced by JB.
Yeah, sure.
I think, is it clear? Okay. So up to what this time I say that first we consider a conductor, then we took one electron and we study the case of one electron, and we hold that, say that in this y direction there is a net magnetic field. So some forces need to be cancelled that net magnetic field. So Mayuga told that, so there appears some induced electric field and it can cancel that magnetic field. And I balanced that two cases here. You can see that here I balanced that two cases. And Faghat told that earlier. Faghat somewhat told. So, but now we can say that Faghat induced electric field is VA into by L. We can say that here it is not L, it is H. Okay. And we instead of that induced electric field, we write that VAB by H, and we solve this equation. We got that whole voltage is nothing but IB divided by net. Okay. So who do I send this equation? Hello? There is no response. Hello, am I audible? Hello?
You gave it to Sanjana.
Yeah, Sanjana
Yeah.
is there?
Yeah.
Yeah. So you can speak up. There is no problem. Okay. IB divided by net. And instead of 1 by NE, I am calling that equation RH. Instead of 1 by NE, just a single term RH. That is the whole coefficient. Actually, we defined that. There is no proof for this defined. Okay. So instead of 1 by NE, we defined some and we induced electric field is into velocity into B, and actually we reformatted 1 by NE into E induced by J times B. So this is what about deriving everything. We'll be stopping this here now, and I'll be resharing that. So I hope this understood. I'll catch another member. Sai Tarun, is that clear? Hello, Sai Tarun. Hello. No. And I will ask another member. Tara is there. Hello. You can speak up. There is no problem. Okay. Hello. Hello. No. No response. Rihiri PV.
Hello.
Yeah. You understood these two equations? Actually, I told 3 equations. I told. Do you understand this?
Yeah, okay, it's clear.
Is that clear? Then what is the first equation?
Wait, which one? Is it about hall voltage?
Yeah,
IB by
hall voltage.
NET.
IB by net. That's
Net.
enough. Okay. Yeah.
And the second one is about hall coefficient. It's 1 by NE.
And
the third one is E induced by JB.
yeah. So you can look here and say.
Okay.
Yeah. So you can see this one. Okay. Earlier I drawn that figure. Now you can say here. Dan, please pick up. Hello.
Hello. Yeah.
In this case, there is an electron here. In which direction electron will be pushed down or push up? In which direction electron will be going?
It will be going. Is it in case of
Please speak up and
equilibrium?
say.
Is it
Yeah,
in case of?
no, due to magnetic field force, where that electron will be going?
It is going to go upwards. Yeah.
Yeah, please think that it is a positive particle will be going down. So electron will be going where?
Upwards. Yeah.
No, positive particle will be going upward.
No,
So
the
negative
electric
particle
field
will be
direction
going.
is downwards, right? Here, it's given like that, right? In here. In the
Oh,
image.
sorry. I told this one. This is the induced electric field. Okay.
Oh, okay. Yeah.
You please.
Yeah. Okay. So it's
leave this.
going to go downwards. Yeah. Okay.
Yeah. So it is going to downwards.
Go downwards. Yeah.
Yeah. All the electrons will be pushed downwards. Yes, Dan. So
Hello.
Mayuga told us earlier, all the electrons will be pushed down. Here, this will be electrons here, right? Hello, Dan. Am I audible? Hello? Hello? Yeah, please leave it. Abarna, can you hear me? You please speak up, okay? Then only I can continue this class.
You're
I
audible,
don't know.
yes.
Yeah. So Ashwin Shekhar, can you hear me? Hello? Please
Yeah.
speak up. Yeah.
You're
So in this case, electron will be pushed down. Yeah, Ashwin?
Yes.
So there, as Mayuga told earlier, there will be a charge separation. As a result, positive charge will be appearing here, right?
Yeah.
So that induced electric field will be coming in this downward direction. This is the same case I told earlier. There is no difference actually. Okay. Is that clear?
Yeah, clear.
Yeah. Now you please hold down. I'll stop sharing. Okay. Please wait, okay. Let me share from here. Yeah. So you can see this one, right?
Yeah, it's
So theory
visible.
I covered. As I told you earlier, I first consider the case of conductor. So now you understood that this whole voltage means two driving force, that is the current and magnetic field we are applying. And Ben told that these two driving force only can affect the charge particles. Yeah. So in the conductor, there is the negative particles, electrons, and the semiconductor also electrons and hole is there. Both these are charged particles. So there is no difference for conductor and semiconductor also. We can apply this Hall effect. Okay. And this two, as this all I described, okay. There is no difference. This all equations I derived. You can please go this through this. Okay, I will share the slide. Okay. And one more thing, RH is equal to 1 by NE. And in the case of semiconductor, we studied the graph of N versus temperature. Hello, Dan. Can you hear me?
Yeah, I can hear you.
So we studied the graph of N and T. We studied, right?
Yes.
So you can easily relate RH and T, right? Because RH is inversely proportional to 1 by N.
1 by N, yeah.
Right.
Yes.
So you can easily relate that to graphs, RH
Graphs,
versus
yeah.
temperature.
Yes, it's possible, yeah.
So I won't be going to that graph. You can please relate. So please connect RH with the temperature. Everyone understood?
Temperature. Yes.
Yeah.
It's clear.
Now you can see the illustration here. This is what I described all till now. So first, we are taking this conductor. This is all as a conductor, not these two pieces as conductor. Okay. This all as conductor only. Okay. This all as conductor. Yeah. And we applied the current so that electrons sorry guys. Yeah. Electrons will be moving in this direction. And we bring this this magnetic field. Here magnetic field is in the upward direction. So you can see that magnetic field is in the upward direction, velocity in this direction. So electrons will be pushed to that side. Okay. As a result, you can see that there is a charge separation. We measured this bottom and top to a multimeter. You can see that whole it is showing some voltage here, and it is positive whole voltage. And you can reverse this direction and same apply here, so that the electron will be pushed to the left side, and you can see that now the whole voltage is negative. Am I clear this? Everyone understood this right now?
Yes, yeah, it's clear.
So you want to learn this whole effect in this class itself. Don't spend another time for learning this. I will show this illustration one more time. You please watch. Okay. So first electrons is there. I apply a magnetic field so that charge separation occurs. As a result, whole voltage occurs. Just reverse, and you can see that whole voltage is negative. Now, till now, I told about conductor and everything. Now you may get confused why I am teaching this whole effect in this semiconductor, right? I will add some more. Okay, some more number. Hello, Kuriakos. Hello. Hello, Kuriakos. Hello. No problem.
Yeah.
Harshita. Yeah, Eldos. So why I am using this Hall effect? Do you get confused? Why I am telling this Hall effect in the semiconductor?
Yeah, somewhat.
Earlier I told this take some conductor and later applied conductor and semiconductor both similar case. I told any confusion you got? Why I am telling this Hall effect in the semiconductor? Why I am teaching this one? Yeah, Eldos Kuriakos doubt is there. Harshida, hello. Harshida, hello. Hello. No. Rebecca Susan. Hello.
Actually, Elias, hello.
Yeah.
Yeah, actually, what do you like? Are you asking why we are learning Hall effect in semiconductors?
Yeah. I am searching that for any idea you have or not.
Because
Yeah,
it's
you please speak up. Okay.
this class is solid state devices, right? So we are trying to study about semiconductors. That's why we are learning Hall effect in semiconductors.
Yeah. That okay. That's only what I just recorded. Okay. So I now telling this
It's
whole
useful
effect in
to
semiconductor.
know about mobility of conductor.
Yeah, I will coming to that. Okay. So I am calling this name. You can speak up. Okay. Let's make this class more interactive. Why I am calling you, please speak up. Okay. No problem. So I'm telling this Hall effect. Now I am connecting this Hall effect to semiconductor, its applications. That is what I told here. So I will give you an activity. You can see this right now. Yeah. I will call one member. So this is an activity. Taha. Hello. No. Whom I will call? Swagat. Hello. You please. Nandana Vasudevan. Hello.
Hello? Hello?
Yeah. Yeah. You can see this picture, right?
Yes.
Yeah. And tell me which type of conductor, semiconductor, N or P? By looking this picture. So Nandana, can you say that?
Yeah. Like,
Can't say. I will give one clue. I will give. So 3, 2, 1, 0. So now you please say that. Which type of semiconductor is that?
N type.
Hello. Yeah,
N
N
type.
type. So you need some external agency to confirm whether it is an N or P. Yeah, Nandana.
Yes.
Why? By just looking, you can't say N or P. Yeah, right?
Yeah.
So this is a one application of Hall effect. So by using Hall effect, you can say that you can identify whether it is an N type or P type, or you may go for what we can say electroscoping level. You may check which electron or holes is more. So that more expensive. The simplest method to know whether it is N or P type is to implement the whole voltage experiment. Yeah.
Okay.
So next application. Yeah, Nandana, hold on.
Elias,
You can know.
is
Yeah.
that through the measurement of RH Hall coefficient?
Yeah, I will be coming for that. You please wait. Okay. Is there any practical idea for showing the presence of negative carriers in semiconductor holes? So while studying that, you said that holes are there. Holes are just simply the vacancy of electrons. If there is a vacancy, then we can say that positive charge carriers are there, right? Positive charge is there. So is there any experiment or the practical idea for showing that? Ashwin, hello.
Hello?
Is there any practical experiment for showing that?
No, I guess.
No. So we can also explain this by Hall effect. Okay.
Okay,
So
okay.
I told two application now. So I told this. So we can say that it is the proof for the presence of positive charge carrier in a semiconductor. Okay. So we can distinguish N and P by using this, and applications N or P is used to find carrier concentration. I will be explaining this. Okay. Now you please identify what all are the applications level. Okay. So this I also told. In the conductor case, I described earlier, all the electrons will be pushed down. In conductor, there is only electrons are there. So why we apply this external agency? We are applying current and magnetic field. As a result, induced electric field appear. Okay. So all the electrons will be pushed down to the bottom of this container. Then there will be a charge separation. That all case you leave. All the electrons will be pushed down. This is the conductor case. Okay. and you can say that you can see this is the bottom of this container conductor, and I am measuring this hold voltage from here only, bottom minus top. Okay, so Amal Raj, hello.
Yes.
So I am measuring hold voltage from bottom minus top, voltage of bottom minus top. What will be the voltage now here? Is it negative or positive?
Negative, I guess.
Yeah, of course, negative. So in this conductor, hold voltage will be negative. So Amal Raj, what is the equation for hold voltage? First equation. Amal, hello.
IB by net, is that what you mean?
No. You please wait. Sanjana, what is the
Aya.
equation? I assigned you that equation.
Hall voltage, right?
IB by
IB
yeah.
by NET.
So hold voltage is negative. So in short, we can say 1 by N is negative. Is there any problem for saying that? Instead of saying
Excuse
hold
me,
voltage is
Elias.
negative.
Can you explain once more how that voltage become negative?
I am measuring this. This you please look that I am measuring the voltage of bottom minus top. Here in this bottom, all these electrons, right? So charge what will be there? All this bottom will be more negatively charged and bottom will be more positively charged. So what is the difference, Ashwin?
Yeah, it will be negative, but
Yeah.
the concentration of electrons at the bottom will be equal to the concentration of positive ions of
No. While applying this magnetic field, all these electrons will be pushed down. As a result, positive particles, not positive charge, will be appearing on the top.
Yeah,
right?
yeah.
So we can say it is a conductor only. Please think that. Okay. So we can measure B bottom minus B top. It will be negative. Yeah, Ashwin.
Yes.
Yeah. So Sanjana, okay, I will come back to Sanjana. 1 IB divided by net. So when whole voltage is negative, we can say that, Ashwin, 1 by N is also negative. Is there any problem?
No.
So we described 1 by N as whole voltage. See, if whole voltage is negative, we can say, of course, 1 by N is a voltage instead of saying that whole voltage is negative. Okay. So you can read this. I showed diagram during the first section, first one. We can read this. So the whole voltage produced in the conductor is negative. Okay. Ashwin, clear?
Yeah,
Is that clear, Ashwin?
Elias?
Yeah.
Why is it necessary to check the voltage like that? We could
I will
always
explain.
check the other way, right?
No, it is taken in this. It is the by convention we are checking.
Okay,
The apparatus also it is placing in that direction.
That direction. Okay, yeah.
That
okay.
Yeah.
But
If it is reverse,
condition.
reverse will get.
Yeah, but this thing would certainly change when we change the direction of magnetic field, right? If we inverse the magnetic
Of
field,
course.
then
Yeah.
Okay.
Yeah. I am taking this as a sample case for our studying only.
Okay. Yeah.
It is not necessary that it should be like that. Okay.
Okay. Yeah. Got it.
Just for understanding. Yeah. Let me know who is this. Hello.
By convention, hall voltage is negative for conductor.
In this apparatus, we are measuring in that way only.
Okay.
Apparatus. There is an apparatus for whole voltage measurement. So in that voltage, we'll be getting that output as that way.
Okay.
Is that clear?
Yeah.
Yeah. So this is what about all conductor. Next, we will be looking into the N-type semiconductor. So in N-type, there will be majority is electrons, holes is there, but electrons is the majority. And we earlier know that electrons will be pushed down. Yeah, Dan. Hello. Electrons will be pushed down. Okay.
Yeah. It's being pushed down. Yeah.
Let me ask one thing. What about the positive particles then? If electrons is pushed down, means what about the positive particles?
It will be moving towards the top. Yeah.
No, you please hold that. Okay. You please look. Here you please assume a positive particle here. Okay.
Yeah.
Then as a case of electron, it is moving opposite to the direction of the electric field. This is the electric current.
Yeah, it's moving like that. Yeah.
So positive particles will be moving to the right.
Yes. Oh yeah. Okay.
So you please look that there is a change in the velocity too. Don't blindly say that it moves up. Okay.
Okay. So the positive particles are also going to come down, right?
Yeah. That is the concept. Okay. Do you get that?
Yeah.
You please assume we took a electron as first here and we shown everything. Electrons, no changes there. It will be pushed down. For a positive particle, the velocity direction is changing. So positive particle also will be pushed down. So done. In this n type, charges is more, right?
For n type, yeah, electrons are more, right?
Yeah.
For n type, yeah.
Yeah. I think there is no class from 11:15. I will be taking 10 minutes. Okay. I want to do some more problems. Okay. So you please stay here. I'll make this section more interactive. Is it interesting?
Yes.
I don't
so
know.
far.
Okay.
Yeah, so far.
I will try my maximum. Okay. You please wait here. I lost that 15 minutes starting. That's the only problem. Okay. So positive particles velocity will be opposite. So positive particles also will be moving down. Okay. Is that clear?
Actually, in
you can
n
respond, no problem.
semiconductor, there wouldn't be any positive charge particles, right? By
Particles
less
not.
amount.
Yeah. Positive particle not. Positive, you can say that actually positive particle is not there. Positive charge is there.
Okay.
But that positive charge can come down.
Yeah. Yes.
Is that the ionized
we can. Hello.
Positively charged particle, right?
No. Dopin, you please leave. Yeah, you can assume that the electrons only. Dopin, you please wait there. Okay. Now we can assume that just as the charge particles. So electrons will be coming down. Positive charge also will be coming down. As we know that majority is negative. So somewhat positive is there. -6 plus 0.02 is negative, right? So some part negative is there, more negative is there, and some positive is there. In general, we can say that bottom will be more negative and top is more positive. So in this case, also whole voltage is what? Bottom minus top. Now, what is Amalraj? Hello. I will call
Can you please repeat?
If I call Amalraj everyone times, it will be boring.
Okay, fine.
I am not familiar with these names. Okay. Ligit, hello.
Yeah.
So in this case, what is the whole voltage? Bottom minus top. What is it? Is negative or positive?
It's negative.
Yeah, negative. So whenever we say whole voltage is negative, we can say that 1 by n is negative. That is whole coefficient is negative. We can say, yeah. Yeah, and you can observe that if it is n type, that sign is also matching. If it is n type, then negative. Whole voltage is negative. We can say this is all conventional. Okay, if conditions are there, this is the conditions. Okay, so next, you can read this. Okay, everything I explained here. And Ridu Rajesh. Hello. No. Reba Pandey.
Actually, she is in the meeting, but she can't unmute, I guess.
No problem. No problem. Okay. Reba Pandey, you can talk up. Hello. No. Anyone? Knife? Yeah. Knife. Hello. No, he also know it. Melvin. Hello. You please speak up. Okay, then I can continue.
Yes, Elias.
Yeah. So we are going to Melvin. You need to help me in this case. Hall effect in P-type semiconductor. Okay. In this case, we told this figure don't change. Okay. Here only difference is what? Positive charge is more compared to negative. Yeah, Melvin.
Yes.
Yeah. Now you please assume positive charge as a particle with an effective mass. Okay.
Okay.
So you can say what is the whole voltage here? So bottom will be more positive than the top. Yeah. Yeah, Melvin.
Yeah, so we are measuring from top to bottom, right?
Bottom to top. Bottom minus top. So what will be? It will be.
Is it positive? I'm slightly confused here.
No. You please think that positive charge particles, you can say with an effective mass, will be concentrating more on the bottom than on the top. Yeah, top also there is positive charge particle. No, if there is
ALIAS?
positive charge particles at the top, then will be negative at the top.
ALIAS, here we reverses the direction of electric field, right?
Induced electric field. This is not the electric field we are applying. Okay.
Yeah, induced
you please
electric field.
consider this is the induced electric field because positive is here, right? Earlier positive was there. Now positive is here. Because in p-type semiconductor, positive charge carriers is more. Is that clear?
Yes, it's clear.
So electric field direction, induced electric field direction will be positive to negative only. This is induced electric field, not the electric field we are applying. Okay.
Okay.
So there is a charge separation. On the top, there will be negative charge as induction. And on the positive, there will be more positive charges is there. So what is the difference? Melvin, hello?
It's positive.
Yeah, whole voltage is positive. So you can please think here, if it is p-type, then that corresponding sign, what is the whole voltage? Positive. And in short, we can say whole coefficient 1 by n is also positive. Yeah? Yeah, right? Hello?
Yes.
Yeah. Next, this is all you can read. I will share the slide, okay? This is all what I told now. Now we will be coming to this application. Now you got some idea, I think. How to identify n-type or p-type? Melvin,
The
hello?
voltage is
We measure the
positive.
voltage, and if it is positive, it is n-type, and negative, it's n-type.
That is only there. Yeah, that's only there. So just take a conductor and perform the whole experiment. If you got the positive, means it is positive. If it is negative, then n-type. That is only the one application of Hall effect. Okay. So you read this. This is all what I
about
written
the case
here.
of a conductor?
Conductor, hello. Conductor hold, I described the conductor in detail. In conductor, there will be only negative charge carriers will be there. So it will be pushed down and the whole voltage is negative.
Okay.
Is that clear?
Yeah. So for the
Okay.
insulator,
Now we are dealing with the semiconductors.
what about the case of an insulator?
Insulator, I will be coming later. Okay, you please hold on. Yeah. Hall effect is used to find the charge carriers concentration. Yeah. So, Sanjana, hello.
Hello.
Please say your equation.
IB by NET.
Yeah. Now you know that I we are applying, so I value we know, B we are applying, B value we know, whole voltage we got from the experimental details, T you know, E and you know. So what is the only unknown there, Sanjana?
Magnetic field, right?
Magnetic field you know from that experiment. Magnetic field we are applying, right?
Carrier concentration.
Yeah, carrier concentration. You remembering that equation, VH is equal to IB divided by net. E you know, T you know that value, I also know, B, VH. Only the unknown is N. So if you got all these details, means you can find the carrier concentration, right? From the Hall effect.
Yes.
Yeah, that is one application. Another application of Hall effect. Next application is Hall effect is used to calculate the mobility of charge carriers. Okay, I'll be explaining this. Okay, let me. This. It is going to finish almost. Okay, only some more details is pending. Yeah. So whole coefficient is 1 by NE, right? Hello. And as I told, you are remembering this equation, right? And I also told that it can be also expressed as this equation. Sorry, E by B. Yeah. Then J is equal to sigma times E. We are substituting for this E as sigma by then what is there? J times, sorry, J by sigma B. Okay. One more thing. Okay, sorry. And I also told that mobility is nothing but what is the mobility equation? Velocity
Drift
by
velocity by electric field.
yeah. So you can connect these two equations. 1 by n is there, and 1 by n instead of I, it is written as this equation. 1 by n I can substitute as I by A times B. Yeah, Ben. Hello. Instead of I by A, this J, right? J by velocity. This is the drift velocity. Instead of this drift velocity, you can write this mobility equation. And you can say that mobility by E times J. And from this equation, you can derive that it is nothing but mu by sigma. Ashwin, is that clear? Ashwin Shekhar, hello.
Yes, Elias.
Yeah. Christina, hello. Christina, hello.
Yeah, it's clear.
You got this equation?
Yeah.
How I am deriving this? 1 by n is there. I substitute for this equation, I substitute and I got drift velocity by current density. Then I substitute this equation, Ben's equation. Okay.
Yeah.
Then I got mobility by conductivity as RH.
Yeah, I
Do you
understood.
understood this? Okay. Then I'll be coming back to this too. Yeah. Let me share this one. Come back to PowerPoint. Yeah. This is the equation I derived. You can see this right now. Okay. And you know that from the semiconductor, Lindemann told that conductivity for a extrinsic semiconductor can be you find out by this equation, and for n-type we can approximate, and for p-type also this can approximate. I don't go into the details. You can substitute interchangeably in this equation. RH is equal to mobility by sigma. Okay. Then now I am coming to Ashwin Shekhar question. Hall effect can be also used for classification of materials. How that can be used? You please see that. Hall effect is 1 by n. Yes, Ashwin Shekhar. Hall coefficient. Ashwin, hello.
Yes, Elias.
Is there Ashwin Shekhar? Yeah.
Yes.
So for insulator, what will be the charge carrier concentration? Amount of charge carriers in insulator will be what?
0.
0. So 1 by 0 is what? Infinity, right? So for insulator, RH will be infinity. Right? Infinity means somewhat higher value, not that infinity. Okay. So if you, while measuring whole experiment, if you got such a large value, it's 1000 or somewhat range, you can easily say that it is an insulator. And for a metal, we can see that charge carrier concentration will be too large and RH will be small. You can search Google that for the RH values. So you can see that for metals, it will be small. And for semiconductor, compared to metal, N will be small. So RH will be large. Is Ashwin clear that details?
Yes, Elias. Thank you.
Yeah. Now some problems we can practice. We all theories all over. Can Christina say this answer? You can please read this. Please remember that current and magnetic field we are applying. Okay, Christina, hello.
Yeah.
I will confirm. You please read this question and try to answer. No problem.
As per Hall effect, should I read it aloud?
Yeah.
Okay. As per Hall effect, if any specimen carrying a current I is placed in a transverse magnetic field B, then an electric field E is induced in the specimen in a direction.
In a direction?
Um.
Please remember that derivation, I applied current and magnetic field where that Hall effect appeared is in the y direction. So I applied current in the x direction, magnetic field in the y direction. Where does the Hall voltage appeared or induced electric field appear? You please remember that equation, the specimen. You please you see this. Yeah, by seeing this, you can answer that question, that figure. Electric field, magnetic field. Where does the induce the electric field direction? Is that parallel to
direction.
what? Yeah, perpendicular to both. Yeah, right?
Yeah.
So you answered that question. Thank you, Christina.
Hey, I have a doubt here.
Yeah, you please speak
You
up.
said like Hall voltage can be used to differentiate between N type and P type, but technically we can't do it, right? Because intrinsic semiconductors also give a negative Hall voltage because it depends on mobility, and electrons have higher mobility than holes. So we can't.
Hello.
If you get a negative Hall voltage, it can mean it's either N type or it's intrinsic.
You can say not. Yeah, N is N type or P type. We can say by looking into the Hall voltage. Yeah.
No, but
problem.
an intrinsic
Actually, that
semiconductor
is
also gives a negative
induced.
negative voltage.
Yeah, but you can. I told that conductor also will get the negative, but you can compare that values. You please look this
Yeah,
up.
I understood everything, but like I said, we can determine whether it's a P type without any doubt. But when it comes to N type, it can either be intrinsic or N type because both
The magnitudes might be different, right? The values of
Ligit. Magnitude will be different. You can
so
go
we
in
need to
detail.
have a comparative standard for that.
Yeah. You can go in detail. Next, I will be explaining. Time is almost up. Okay. So Ligit, you can please read this question and answer. It's very easy, right?
Yeah, and all effect which of the following is true.
Actually, what we are applying in the Hall voltage from our side, what we are applying?
Magnetic field is applied, electric field is induced.
Yeah, electric field is induced. Okay, is that clear for everyone? Dan, hello.
Yeah, it's clear, Elias. Yeah, it's clear.
Yeah, electric field. So you can do this problem. Okay. Yeah, what is the relation between mobility and conductivity? Yeah, Dan, hello. You can please answer this.
Yeah, mobility and RH factor, right?
RH is mobility by conductivity, right?
Yeah, mobility by conductivity, yes. So mu by E, so mu into A will be the answer.
Yeah. So this question, can you please look? One more question remain. I will be doing this question. Okay. So let me wait, guys.
Elias,
yeah.
I think it would be better if you provided the slides with the answer. So since it's too late now, can you do that? Is it okay?
Yeah, I'll be doing that. I think 11:30 is there almost.
Yeah,
okay. So you can do this problem. I think this is only somewhat difficult. All that remaining problem is just in the substitution only. Okay.
Yeah, substitutions only. Yeah.
So thank you. Is that clear? Everyone understood what is Hall voltage? I think I was able to answer most of your doubts. Is there any more doubt? Means you can DM me WhatsApp. Okay, I'll be answering that.
Yeah, thank you, Elias. It was really nice. Yeah, it was very good. The session was very informative.
I tried to make that section more interactive. Is that good or bad?
Yeah, it was certainly good. Yeah.
Otherwise, I will be telling some equation. You will be sleeping some side. So thank you, everyone. Yeah. So you can leave now.